Hello everyone! Thanks for joining the second part of the video What? Mobile Networks. In the first part we discussed historical prerequisites and evolution of mobile networks. Let's move deeper into mobile networks details. First thing you likely noticed when we talk about network evolution, a lot of efforts were made regarding data throughput increase via mobile network, since packet data introduced in 2G networks. We need to spend a couple of minutes to understand what is underneath packet data term. Simplified, any information to be sent is kind of chopped into very small portions named packets, and each packet sent and travels independently from sender node, maybe through several transit nodes, and reaches receiver node where all packets eventually are combined to form initial message with 100% the same content, which was held by sender node right before chopping and sending. Even though packets at the beginning and at the very end form the same block of data, each packet travels independently and potentially may even use different route than any other packets. Routes don't matter as long as all packets reach receiver node. Couple of important things why such design was made. First of all, we can use shared resource to send packets between several senders and receivers without reserving the whole channels for just one sender and one receiver for the duration of data exchange. Imagine one small packet between one sender and one receiver quickly traveled through a channel, and right away this channel is free to transmit next packet between same or other sender-receiver pair, and so on. Packets transmission within the same channel is scheduled to separate packets by time. That consequently allows to better utilize limited resources, transport channels. We need to realize that sender and receiver not constantly exchange data of high volumes. It might be just a small email sent once in a while, small spike of data load, and after sending email, such shared channel can be used by others. We can compare packet data approach with different so-called circuit-switched approach. First-generation networks used circuit-switched type for voice service based on channel reservation, all the way between just two mobile phones. It does not matter are people currently speaking using phones and mobile network therefore sends voice data via that reserved channel, or they just silently breathing half an hour without actually loading a channel. Channel will be reserved for the duration of the call for just these two subscribers. That is about bad network utilization without sharing resources, which was fixed with packet data approach. Second important thing coming from flexibility of route choosing per each packet. Redundancy of transport channels can be introduced, which means more than one route is available between nodes. If you have a temporary overloaded or broken channel, packets can be rerouted through alternative route or routes. A part of redundancy when one channel may be loaded very high while others are used occasionally, which may lead to packets collisions, rejects and retransmissions. Alternative approach named load balancing can be used to utilize alternative routes more evenly. Packet data design allows to use redundancy and load balancing naturally. Question is, how effectively packet data transmission is used in mobile networks? First, let's imagine how mobile network is physically constructed. Simplified, it has hierarchical structure and looks like a tree. There is an army of mobile phones roaming in a large geographical territory. We can compare them with tree leaves. Hundreds or thousands of phones can be within coverage of just one base station, which can handle traffic to and from them. Base stations can be compared to tree branches on the level closest to the tree leaves. Mobile phones and base station talk to each other using wireless communication over the air. All base stations form a radio access network or RAN subsystem of mobile operators network. Can mobile network be represented by just base stations? What do you think? If your answer is no, you are absolutely correct. Main function of base station is just to implement so-called last mile wireless communication towards mobile phone. Base station is not taking care of high-level service to be provided to end users. For example, it has no idea how to provide packet data transmission, which we were currently talking about, or voice service. Other mobile network nodes take care about handling services themselves. Services are usually unified through the whole network, meaning that wherever customer travels, thousands of miles apart, but still under mobile network coverage, the same service, like packet data transmission, can be still provided to him. Since services are unified, just few nodes inside mobile network, directly or indirectly connected to lots of base stations, can provide such services. Most of such centralized nodes are part of so-called mobile core network subsystem. Exact ratio of base station numbers to core network nodes number depends on particular network and node's capacity, but it can be high enough. Just to feel real possible numbers, less than 10 core network nodes can handle thousands of base stations. Let's wrap up. We may have thousands of our tree leaves, mobile phones, connected to their last level tree branch, base station within RAN subsystem, and hundreds, thousands of last level branches connected to a larger branch closer to a tree root, mobile core network subsystem. Sometimes tree can grow a lot, so capacity of each branch may become not enough to send all nutrients, network traffic. In this case, additional branch of the same functionality can be added to prevent network parts overload. But overall hierarchical tree structure would be still in place. The closer to the tree leaves, the smaller capacity is needed. But imagine packets coming from thousands of phones aggregated on the base stations, and then from thousands of base stations aggregated on certain core network node. More and more packets are expected at core network part. So the closer to the tree root, the more traffic throughput needs to be handled. Some network parts around modern core network nodes, central part, usually have hundreds of gigabits per second capacity planned upfront, and such nodes likely connected using high-speed mediums like optical or copper cables, which are different from generally slower radio resources used between phones and base stations. Look at our tree. Imagine you need to send high throughput data from one mobile phone all the way to some destination outside of mobile network, google.com or cnn.com web server, for example. And imagine that all parts of network were planned accordingly with higher capacity closer to the core part. The slowest segment on the way can be named as a bottleneck. And overall end-to-end throughput is limited by throughput of the bottleneck. Analogically, you can imagine crude oil pipes connected consequently one after another. The pipe with the smallest diameter, among others, has the minimum capacity on the way from end to end. And even though other pipes can transmit more oil per each second, overall throughput will be downgraded to the throughput of that slowest pipe, which is the bottleneck of the whole system. Historically, radio resources have been a bottleneck in the mobile networks. What radio resources? I'm talking about last mile communication between base station and mobile phone. And therefore lots of efforts were focused on increasing throughput of such bottleneck. As a result, overall throughput increase for packet data transmission from older to newer mobile networks generation was achieved mainly by increasing throughput of radio resources. That was briefly about packet data and working on last mile bottleneck throughput increase. How exactly evolution of radio resources have been happening with focus on increasing data throughput? There were certain distinct technological enhancements made. Let's check the most interesting of them. First, we need to discuss some terms and limits set by Mother Nature and explored, described by laws of physics. Communication over the air goes via radio channels. We will discuss what a radio channel is in a moment. Like pipes delivering oil have certain diameters to achieve required throughput of oil, radio channels also have throughput limitations set by their so-called bandwidth. What is it, bandwidth? To answer, we need to start with another term. Any signal sent over the air has its characteristics named frequency. For easier understanding what it is, let's imagine a wave, for example waves on the water surface, if looking from a side and imaginary cut. Mathematically it resembles a sinusoid. Waves make certain amount of swinging, also named oscillation, per each second while traveling from a source generating this wave. This is an example of one oscillation cycle between two neighbor peaks. This is another oscillation cycle between the similar peak points. Number of such cycles per second is named frequency. Unit for describing frequency named hertz. For example, 100 cycles per second represents frequency of 100 hertz. Our eyes could see waves on a water surface, but they could not see lots of other waves, including radio waves and sound waves. Luckily, our senses of perception were extended by developed technological devices. So we can see invisible for our eyes waves through special monitors of certain devices. For example, radio waves, sinusoid and frequencies values could be seen using oscilloscope device. Sometimes for better understanding and side-by-side comparison, different frequencies could be drawn in books with different density of cycles. The higher the frequency, the closer to each other and consequently more oscillation cycles within the same area are drawn. It actually makes sense because radio waves have electromagnetic nature and have the same transmission speed over the same conditions regardless of their frequencies. For example, in a vacuum, their speed equals to the speed of light. So two radio waves of different frequencies will travel the same distance within the same 1 second. As a result, wave with higher frequency will have more cycles than wave with a lower frequency per second. In some science museums, I saw graph with XY axis, where x-axis was for frequency values, and for better visualization, they made kind of side-by-side abstract relative comparison by cycle density, not showing actual sinusoids or even at a proper scale though. Frequencies ranges from 0 Hz through kilohertz, 1000 cycles per second, megahertz, million cycles per second, gigahertz, billion cycles per second. Now, interesting thing. When we need to send data over the air, we need to use not precise frequency, but actually frequencies interval, like a small slice with a range of frequencies from our endless graph pictured a second ago. This slice will be assigned to a radio channel for data transmission. And a range of frequencies represents such a radio channel bandwidth. For example, bandwidth of this radio channel is 150 MHz. Now coming back to data throughput topic, within a task to robustly deliver data over the radio, regardless of radio conditions. The main idea is, the wider the radio channel bandwidth, the higher the data throughput could be potentially achieved. This comes from Nyquist's theorem about sampling of digital signals, which is out of scope for this video. Bandwidth is the key and starting point for our data throughput discussion in mobile networks radio channels. Simplified, we have direct radio, I removed coefficient for now, with not precise but simple examples for understanding to start with. 100 MHz bandwidth could give up to 100 megabits per second throughput. 20 kHz bandwidth could give up to 20 kilobits per second throughput, and so on. That's why actually mobile operators are battling for radio channels to be allocated for them, which are in most cases licensed by state governing bodies. The more total available bandwidth, the more data throughput and consequently better end-user service can be provided by operator. For those who plan to dive deeper into radio channel allocation and bandwidth, I'll give extra information. Do you remember that we may have bidirectional data transfer? Remember term duplex mentioned earlier. Information not only needs to be delivered towards mobile phone user, but also could be sent the other direction from the user. When you talk, decoded voice data sent to and from user. Therefore, two separate resources, not to disturb each other, should be allocated in mobile networks for each of two directions for data sending at the same time. Direction from mobile user with relatively small height towards tall tower with base station antenna called uplink direction, and direction from base station towards user called downlink direction. When radio channels are allocated, two frequency slices, each having certain bandwidth to be allocated, one for uplink and another one for downlink direction. Wrapping up, our frequency interval or bandwidth of radio channel initially determines maximum data throughput, similar to oil pipe's diameter affecting oil max throughput. Bandwidth is the first important item with an evolution of radio resources topic. Second enhancement with radio is about ways of effective allocating resources, for example more bandwidth, to achieve higher end-user throughput. Second item came into picture when packet data was introduced, and one channel for transmitting information can be used as a common channel for several users. At the very beginning it was not a case. In 1G mobile networks, each channel was allocated per just one user. There were some exceptions, but let's omit them now to be focused on non-shared resources allocation. That means the whole channel bandwidth on uplink and downlink directions was given to a one user. Who wants to learn more can read about term FDMA, Frequency Division Multiple Access. Simplified idea of FDMA is that large radio bandwidth allocated for radio transmissions from all users. And this large resource is divided into list of limited number of narrow radio channels. Each of such channels has its main frequency in the middle of imaginary bandwidth and can be potentially allocated per any user. So multiple users can jump to use network resources at the same time on different channels, each user on its channel. Sometimes instead of bandwidth with start and end frequencies, they use channel main middle frequency and term channel spacing. Remember our previous topic about packet data transmission, about small packets from potentially several users sent over common channels. In second generation networks, another TDMA technology was introduced on the top of FDMA, which allowed to share common radio channel among several users. TDMA stands for Time Division Multiple Access. Simplified, it means that data sent over one radio channel is sent in a pile of packets one after another. Some packets are allocated for first user, next packets for the second user, next packets for third, and so on, up to maximum number of users allowed. Allocation of so-called time slots is looped within cycles. After resources allocated for the last user, next packets will come for the first one, and so on. In GSM mobile standard, up to 8 users can jump per each radio channel. For an analogical example, you can imagine that FDMA technology allows to put pair of users into each room for communication. TDMA technology can be imagined as 8 pairs of users talking in the same room. But each pair of users is given short period of time to talk. Then next pair is shortly talking, and so on. Eventually, each pair can glue the whole conversation from its small portions. In mobile phone, there are a lot of such small packets coming within each second, way faster than people can pronounce words. An additional trick that for data transmission in TDMA technology, more than one time slot, for example out of 8, on each radio channel can be allocated for the same mobile phone, which allows to dynamically increase data throughput per user. Multiplexing, meaning combining several time slots at a time. The other technologies appeared later, for example WCDMA, Wideband Code Division Multiple Access in third generation mobile networks, and OFDMA, Orthogonal Frequency Division Multiple Access in 4G and 5G networks. WCDMA uses wide bandwidth, not chopped into narrow radio channels like it's done by FDMA. Channels are divided by special mathematical codes. Remember analogies about FDMA and TDMA. Analogically, you can imagine WCDMA as a large building without any small rooms, narrow radio channels, but rather like open space of the whole building. Lots of people are talking to each other at the same time. It sounds like a lot of noise, but people can hear each other in pairs because each pair uses separate unique code, foreign language, known only to that pair and not to others. One mobile phone may use several codes at a time to increase overall data throughput when needed. OFDMA combines some principles of previously discussed technologies and additionally uses techniques of allocating radio channels being denser, closer to each other, compared to FDMA from previous generations. In older generations, large channel spacing was used between radio channels to avoid interference. What is radio channel interference? We also can call it noise. Imagine that two pairs of people are loudly talking in the same room at the same time, very close to each other. One pair may interfere discussion of another pair. That means words of one pair could be even not recognized because another couple is so loud. From a reliable data throughput perspective, that means in order not to miss any single word, we need to somehow recover missing information. In the simple case, missing word needs to be pronounced again. So we spent twice more time on sending word, and overall data throughput, amount of data per time interval, therefore will go down. As a workaround, it's better to put pairs of people aside so their loud talking won't disturb neighbors. Similar things are happening with radio transmissions. Interference may lead to the worst case of data retransmissions, which downgrades throughput. Some interference you can predict from the very beginning, when planning radio channels and further allocation. As a result, neighbor radio channels spacing was introduced in standards. But for OFDMA, they made discovery allowing to keep neighbors closer to each other because of some physical orthogonality principles, which allows not to disturb noisy neighbor talkers. Additionally, information from mobile phones are divided into very small chunks of data. And when mobile phone receives data, small chunks of data for one phone are spread among many subchannels. And moreover, they are spread by time. If noise over the air would happen on a certain frequency, it won't affect information sent on other frequencies. Or if noise would happen during certain time, it won't affect information sent before or after noise spike. That allows to reliably send data with even higher throughput than ever before. That was very brief intro, and you are very welcome to read deeper about FDMA, TDMA, WCDMA and OFDMA, and maybe other types of radio resources allocation yourself. Main idea behind using these technologies is to multiplex resources, meaning to use several of them at a time, which leads to having more aggregated bandwidth for end user, which in turn increases overall data throughput per user. Third enhancement with radio is about ways of kind of squeezing throughput over the radio. I would compare it to archiving data to have less data to be sent through limited radio resource. Big size of data could be seen as archived at a time right before transmitting radio signal and extracting from archive original amount of information at a time of receiving radio signal. How is it possible? First of all, we need to remember that we live in a digital era and information transmitted between network nodes on wires or over the air is represented in binary form. Who are not yet familiar, we recommend to watch our video Binary Numbers and Binary Data. In short, any information can be coded by sequences of binary numbers, which can be only in two states and represented by two values, marked by convention as 0 and 1. Over the air, we can send only analog signal in the form of sine waves. Digital bits are modulated, meaning represented over the air using analog sine waves. And both sender and receiver know how to map or correlate modulated analog signal to digital bit 0 or 1. Another important fact that information sent in equal time intervals. Such interval named tact. Both sender and receiver are precisely synchronized to know when each tact occurs. Initial implementation was every such tact transmits just one binary digit or shortly bit. That was initially the case, before squeezing information, which we are about to discuss. We cannot increase tact number per second. It's determined by radio standards and frequencies used. The only way to increase throughput is try to send more than one bit per one tact. The idea is hidden in a trick of signal modulation, physical phenomenon. Simplified, if we look into our purified sinusoid signal, it can be somehow distorted, intentionally changed by rules known to both transmitter and receiver. For example, we can shift our sinusoid signal kind of to the right for the duration of the tact. This is named as phase modulation. One of the possibilities is to have 4 distinct states of such phase shift. Here they are. Mathematically, they are shifted to the certain value. And for easier representation of our 4 distinct values, convenient corresponding graph could be used, showing main thing, how sinusoid was rotated to the right according to those values. This value, which is about the smallest radial angle, meaning we moved to the right a little bit, corresponds to this sinusoid. This value corresponds to the next sinusoid with higher so-called phase shift, and so on. 4 distinct phase shift states allow to send 4 distinct combinations of 2 bits, 00, 01, 10, 11. Such modulation, allowing to send 2 bits per tact, was named QPSK, Quadrature Phase Shift Keying. This is an example of using properties of analog signal transmitting to map more digital data. If you have 1 million tacts per second, with 1 bit sent per tact, you have 1 million bits per second throughput. With QPSK modulation, you increases throughput twice, in our example till 2 million bits per second. In binary world, we can have max of 4 unique combinations of 2-bit sequence. There is no 5th 2-bit combination available. 4 is the max. So it's enough to have 4 distinct states in our modulation to send 2 bits. Similarly, to send 3 bits combination, 8 distinct states are required. For 4 bits, 16 states. All these examples show that distinct states can be calculated as a 2 power by number of bits to be sent per tact. Why I mentioned mathematical operation power? Because other modulations were introduced after QPSK, and number of distinct states is usually embedded in names of those modulations. Some examples are 16 QAM, 256 QAM, 1024 QAM. And you can understand how many bits per tact each modulation can transmit. The first one is about 4 bits, second example 8 bits, third example 10 bits. These are examples which were evolving along with mobile networks generations. The last example, 1024 QAM, expected to be introduced over the air for 5G mobile networks as it was announced at the beginning of 2020. Small comment for those who plan to dive deeper into modulation. QAM stands for Quadrature Amplitude Modulation, and additionally to phase shifting, amplitude of signal or signal strength is also changing. Combinations of phase and amplitude shifting allows to achieve even a larger amount of distinct states. Look to the graphs and compare with one for QPSK. If compare these 2 dots, they are both about the same phase shifting, but with different signal strength, and different dots represent different bits combination. Wrapping up subtopic about modulation technique. It allows to have coefficient which our throughput over the air can be multiplied by. This coefficient allows to send more bits per second than number of tacts per second. It analogically looks like you have compressed amount of data exactly over the air with original high throughput on both sides outside of the air. And these modulations are evolving together with mobile networks generations. Fourth enhancement with radio. Improvement measures were done to provide even more bandwidth to the end user. Carrier aggregation technique was introduced mainly in 4G networks to be used in LTE standard and onwards. Before CA, subscriber was receiving resources from just one wide channel, named also component carrier. Such carrier has some standardized bandwidth. Just FYI, carrier with 20 MHz bandwidth available. Remember simplified mapping bandwidth with throughput. CA allows to allocate several carriers for one user and thus aggregate total throughput per user. The first KA implementation had 2 carriers aggregated. Later, up to 5 per user became available. The more total bandwidth, the higher throughput per user. Remember? To simplify, signals from different frequencies can be multiplexed and sent even using single antenna with carrier aggregation technique. MIMO is another separate technique introduced. It stands for multiple input and multiple output. General idea is to use multiple transmission and receiving antennas, even to send data on the same frequency at the same time to the same mobile phone. We already discussed time diversity using TDMA, frequency diversity using FDMA and OFDMA. MIMO is an example of spatial diversity. Antennas are generally located at some distance from each other and send physically different signals. Why is it needed? Initially, it was made to increase chances to more reliably deliver data, completely duplicated by each antenna, by sending absolutely similar redundant data via both transmitter antennas. Think about this analogical example. You can experiment with your home stereo audio system, which has 2 audio speakers, or configure yours to work with just 2 speakers for a while. You have analog of MIMO system with 2 transmit antennas, 2 audio speakers, and 2 receiver antennas, your 2 ears. You can experiment with speakers positions, which affect direction of signal sending. You can turn around yourself or move in a room. You can put some obstruction between one of your ear and one or both speakers. There are higher chances that at least your one ear could hear music better and you recognize all details, instruments and voices transmitting at any point of time. So even another ear may have issue with signal receiving. Initial sent information would be more reliably delivered. In radio transmission, similar obstructions could happen. While one path between at least one transmitter and one receiver antenna could successfully send the signal directly or reflected. Even if both passes may be somehow impacted, signal usually transmitted with extra information to have capability to mathematically detect errors and recover originally sent data. Later, MIMO started being used to send not duplicated but different signals through each transmitter antenna, for example by using phase shifting to separate signals sent by different antennas. That allows to increase throughput by multiplexing throughputs of more than one different data channels. Analogically, you can think about your stereo system. Different signals could be sent through the left and right audio speakers. Our left ear receives different information than right ear for a good stereo signal. And our brain multiplexes signal the way that you can perceive instruments as located in different places around you. That's how your brain receives excessive information in stereo mode through 2 incoming channels, left and right ears. In 4G LTE system, up to 4 antennas at transmitter and up to 4 antennas at receiver sides could be used. So if different signals are sent through transmitter antennas, overall throughput per user could be increased, if to be focused on throughput. In 5G massive MIMO, beamforming and beam steering techniques were introduced. Massive MIMO is an extension of MIMO with use of large antenna array. They might be 16 per 16, 64 per 64, where the first number is about transmitting antennas number and the second number is about receiving antennas. Regarding beamforming technique, let's start with some history. 1G mobile networks used omnidirectional antennas, meaning that signal from them spread out in all directions around, covering kind of circular geographical area, like electric lamp spreading light around if it's not obstructed by any cover. In 1G networks, we are talking about shape of horizontal coverage taking care of enough distance, approximately up to 40 miles in radius. Any mobile phone within that coverage area is able to communicate with base station through that antenna. New subscribers were joining operator networks, and to handle increased capacity, base stations started using sectors with several antennas with a sector-shaped radiation patterns. Direction of signal is more narrowed, like flashlight lighting only with certain direction ahead. Simplified, if each sector radiates a radio channel with one frequency, then if you have 3 sectors per base station, such station can simultaneously handle 3 times more subscribers than with omnidirectional antenna radiating one frequency's radio channel. This is because standards clearly specified maximum phones allowed being handled per radio channel. Do you remember we mentioned up to 8 users per channel in GSM? Now we are coming to beamforming in MIMO. Among other characteristics of signal sending, like signal strength, phase shifting and others, separately I would mention also very narrow horizontal sector shape radiation. It can be compared with some flashlights which can optically send very narrow light beam instead of illuminate everything in the front. Such beamforming allows to communicate precisely with specific mobile phones without covering a large geographic area with lots of other phones. Next improvement is beam steering technique. It's not only about using narrow directed beam, But antenna arrays are also able to change the direction of signal radiating for such beam, following mobile phone to be always radio connected regardless of its movements. If we have lots of antenna elements within array, one of the possibility of beam steering is to switch antenna elements where each element has own direction different from adjacent antenna elements. Analogically thinking, it's like using flashlight to put light on some animal near your camping site at night and change direction of your light beam to follow that animal while it's going away. And the fifth enhancement with radio I want to mention within the topic of increasing data throughput over the air. It's about frequencies used in different generations. In 5G networks, possibility to use so-called millimeter waves was introduced by MobileNetworks. When they talk about millimeter waves, that means very high frequency signals. In 4G, LTE standard uses frequencies around 2-3 GHz. Millimeter waves start from 24 GHz and above. Here's the trick. Let's return to the very first item we mentioned. The larger radio channel bandwidth, the higher data throughput we can achieve. In LTE, radio channel bandwidth can be up to 20 MHz. While with extremely high millimeter wave frequencies, it's possible to allocate radio channels with 400 MHz bandwidth. Technically, only with just bandwidth we can achieve potentially 20 times more data throughput values. In short, higher frequencies, especially in 5G networks, bring radio channel with extremely larger bandwidth, consequently enabling higher data throughput. That was about the topic of radio resources evolution with focus on data throughput increase from first generation mobile networks. We mentioned few items having direct impact on potential throughput. First discussed item was radio channel bandwidth, which simplified has direct ratio to data throughput. In short, for high throughput, wider bandwidth is needed. Recently we mentioned fifth item, which is specifically applicable for 5G mobile radio, when we showed that very high millimeter waves radio frequencies allow to chop radio channels with very large bandwidth, several times higher than in the previous mobile network generations. That is a basis for initial very high throughput. Second item was about effective radio resource allocation, where we discussed FDMA, TDMA, WCDMA, OFDMA resource allocation possibilities. Important aspect here is, when we have multiple subchannels available, it would be possible to multiplex several of them to use at a time per single mobile phone. The more resources are combined, each with its own bandwidth, the high throughput can be achieved for end user. Third topic was about signal modulation, which we analogically compared with information archiving. We mentioned that over the time, QPSK, 16 QAM, 256 QAM, 1024 QAM, and other modulations become available, allowing to send several bits per each tagged, which in turn increases overall end-user data throughput. Fourth item was about several different techniques, like carrier aggregation, when in 4G LTE radio up to 5 carriers with 20 MHz each could be aggregated for one end user. MIMO was the next technique, allowing to simultaneously use up to 4x4 antennas on both transmitting and receiving sides. It helps with interference and also allows to increase data throughput when different signals sent through different antennas. Massive MIMO with large antenna arrays, beamforming and beam steering techniques were next improvement, which can be seen in 5G networks. I also want to strengthen out that all these items may be used in combination. We can have very large radio channel bandwidth on 4G and 5G radios, and at the same time we can multiplex resources within your resources allocation technique, like OFDMA. We can use advanced modulation like 256 QAM to increase throughput several times on the top of that. We can also use MIMO in 4G or massive MIMO in 5G, which also can improve end-user throughput. In this second video part, we were focused on radio resource evolutions. Now you know a lot of techniques and terms to dive deeper if needed. Are you interested to know what's inside mobile networks? Then see you in the next third part of the video.